All right. This is chapter 18, aromatic reactions. So first, we're going to take a quick look at the general mechanism. So we've gone over a couple of different types of mechanisms throughout organic chemistry. And when we do that, we want to try to categorize them, right? So this is the next category. These are the benzene reactions. So this is an electrophilic aromatic substitution reaction. So we have a benzene ring, and essentially what's happening is we're replacing one of its hydrogens with an electrophile. Um, this general mechanism is as follows. So we start with benzene, we attach the electrophile to it. This is the slow step because you're breaking aromaticity. And if you recall from 109A, aromaticity is just when you have a conjugated system, an odd number of electron pairs, planar, whatever. It's just a really, really stable structure. And when we break it, we lose that stability. So that's why it's slow. And then the deprotonation to restore the double bond is fast because we're regaining aromaticity, right? Is we're increasing the stability. Okay, bromination and chlorination. So this is there are three different halogenations of benzene we'll go over. So the first two are brominations and chlorinations. They effectively are the exact same, and you'll find that all the EAS reactions we do in this chapter and the next chapter when we go over heterocyclic compounds are approximately the same. Anyway, so FABR3 is a Lewis acid. So what is a Lewis acid, right? A Lewis acid is this compound here. So what's happening is we have an electrophilic Fe, and the Br2, one of the BRs is attacking this Fe, and we're creating this structure, which is basically just making this whole part of it a really good leaving group, such that our benzene can attack at this Br, kick this off, and slow step. Then we restore aromaticity, we get our final structure. Exact same reaction mechanism for chlorination. And you'll find throughout this chapter, we'll be going through the same general mechanism of generation of an electrophile, attachment electrophile, and restoration of aromaticity. There's nuance here and there, but it's approximately always like around that vibe. All right, iodination. So iodination is a little bit different. It requires a lot harsher of conditions. And you're not really on the hook for the mechanism for the electrophile formation. This is approximately what's going on, though. But essentially, the reason why it requires such harsh conditions relative to Br and Cl is just because the I two is I is like iodine is really, really big, right? So the bond between them is such that if we tried to use a Lewis acid, it wouldn't become a strong enough electrophile. So all that to say is, like just know that iodination is a little bit different than our regular run-of-the-mill halogenations. All right. But again, same characteristic mechanism reaction where we have the benzene attack, break aromaticity, slow step. Then we have restoration of aromaticity, fast step. Cool. Okay, nitration of benzene. So again, it's the exact same mechanism that we're going to see over and over again. We generate our electrophile, nitronium ion, which is just NO2 plus. In most of the generations of the electrophile, what basically happens is we have some type of acidic conditions, and the electrophile that we're trying to form will before have a water that effectively leaves, right? Like, so what we're doing here is we're adding an H here, and now we have a water that's going to leave, and that gives us a positively charged compound. All right. And then once we have that electrophile, attack, slow step, deprotonation, fast step. Cool. That's all it is. Okay. The sulfonation of benzene. Again, it's pretty similar to this. There is one slight caveat to this. The only difference, the big difference is that this reaction mechanism is actually reversible. Interestingly enough. Um, yeah, I mean, anyway, you're not really, on the hook to know like why specifically it's reversible. It has to do with the energetics and electronic structures associated with it. I mean, I guess it's also just to say that like it's the same reason that adding water, adding an ester to a carbonyl compound is reversible, right? The steps that we take to get there are relatively flat. But anyway, right. So formation, EAS, cool. Yeah, and I mean this is just showing you how to reverse it. Again, you're not on the hook for the mechanism, but it's relatively straightforward. Okay, Friedel-Crafts acylation of benzene. So What again we're doing here is we're starting with the benzene, and now we're starting with acyl chlorides and acid anhydrides. All right. So we're going to use a strong Lewis acid, AlCl3, and water to add this acyl chloride or acid anhydride. The mechanisms are approximately what you would expect. The first one, the Cl attacks here. This group immediately leaves because, again, if we recall from last quarter, it's just such a good leaving group. And we form the ion here, which is our acylium ion. It's our good electrophile. And then approximately the same thing with the acid anhydride. I mean, the only difference is the electrons have to come down, and then there's a couple more arrows, right? Just because it's not as reactive and not as good of a leaving group as chlorine. But anyway, once we get to that point, there's a carbon here, right? And this O is has a plus charge, which means it's withdrawing electron density, which means this spot is a really good electrophilic spot. So we'll attach here, we'll kick up these electrons. So this is the slow step, deprotonation, fast step. All right. So the reason why we need an aqueous workup step, the reason why we see like H2O, H2O, you know, okay, I guess just those two, is because of the fact that AlCl3 will actually complex with the O if we have excess AlCl3. So to remove the H2 or to remove the AlCl3, we need H2O. So just one of the practical considerations of what's going on in this reaction, like what we have to do in real life. Okay, Friedel-Crafts alkylation of benzene. So alkylation and acylation are pretty similar. The only caveat to alkylation is the fact that we go through a carbocation-like mechanism, which means we are subject to carbocation rearrangements, right? Um, so let's go through it, right? So excess benzene will give a simple alkylation. We use excess benzene to make sure we don't chlorinate the benzene multiple times. So if you used excess of RCl or AlCl3, those together would give di or trichlorinated benzenes. So we just use excess benzene to make sure that we get a majority monochlorination product. Okay, and then alkyl Cl, Bri will all work. Just don't use vinyl or aryl halides. It's too unstable. There's a different way that we do that. Formation of the electrophile, cool. Um, and sometimes it doesn't matter, right? Sometimes if we have like a really simple alkyl chain, then you'll get what you want. But oftentimes when we have like a long alkyl chain like this, we're gonna get a carbocation rearrangement, and this is gonna be our major product as opposed to this, right? And we'll go over strategies of how we go about getting this as a major product. And spoiler, it's just gonna be we're gonna be using an acylation reaction, and then we're gonna be reducing the carbonyl off a bit. All right. Alkylation through acylation and reduction, right? So all we're doing is we're adding our acyl chloride. Once we get it here, we reduce it. So we remove the carbonyl compound, ACO, and this is our way for us to prevent rearrangements, right? Because the way it'll work is we'll form a plus here, and this plus will not be able to rearrange because it'll be like right on this point, and the oxygen will prevent it from doing so. Okay, Wolff-Kishner. Wolff-Kishner is another way to reduce carbonyls. So, I mean, it's just a little bit milder of a way to do so. It does not reduce nitro groups. Palladium carbon reduces nitro groups if you need to. Um, I don't believe you're on the hook for the mechanism for this, but it's not too terrible if you looked it up on Google. It's just kind of your run-of-the-mill tetrahedral formation with the little caveats here and there. All right. Alkylation through coupling. So this is a palladium coupling agent that you guys didn't learn this year. You might learn in future years, but this is an organoboron compound. I guess all you need to know is when you have this reagent and palladium L2 with basic conditions, you'll get a coupling right onto this position. So it's a way to add groups aryl or vinyl. Yeoman's reagent is another way to do this. This is a reagent that you're more familiar with. We have our benzyl or bromobenzene, and we have an organic cuprate, so we'll attach it right at that position. It's exactly what you'd expect. Okay, cool. Reactions of benzene substituents. So there's a lot of different reactions that we can do, especially after we install groups onto the benzene. You recall from 109B, we can just do a halogenation, radical halogenation. We can use NBS if we want to be very specific about where we place the BR. Reductions, if you want to just reduce a double bond, you can use H2 palladium and carbon. Raney nickel will reduce the CN to an NH2 amino group. So benzylamine. Um, H2 palladium and carbon will reduce a nitro group all the way down to NH2. Um, it's important to note here that Wolff-Kishner reductions will not reduce nitro or alkene groups. So again, that's a good question to ask. They reduce carbonyls, but they cannot reduce those specific groups. Okay. Um, this I believe is the only like way that you'll learn to reduce a benzene all the way down to a cyclohexane. And it makes sense that you'd use nickel, you'd use really high pressure and very high temperature, just because benzene is a very, very stable compound. And I don't think you're on the hook for this mechanism either, so it's just sufficient to memorize the reagents and conditions associated. All right, oxidation. So you'll recall that the chromic oxidation agents are the strongest ones, so they'll reduce all the way down. Um, so it's important to note here that you need at least one benzylic H to oxidize, right? So you can see here that there's no benzylic H's at this point. There's hydrogens here, here, and here, but those aren't benzylic, right? We need them to be right here, right on the connection. So we can't oxidize that, but we can oxidize the rest. And kind of something interesting that we see here that we hadn't really seen before is the fact that, if we have a 1, 2, 3, 4 carbon chain, we'll basically lose 3 carbons, and we'll install carbonyl O and OH. So that's really something you haven't seen before. So I would take very important note of that. It's the reason why it's different is because it's a benzylic position. Sorry. And as I'll like always say, like resonance and conjugation, those are always the things that make exceptions for everything, right? Okay. Nomenclature. So the monosubstituted benzenes to know are toluene, benzaldehyde, benzoic acid, phenol, anisole, and aniline. I think that this is a relatively good list. Obviously there are formal ways to name these compounds, but like this is methylbenzene, right? This is hydroxybenzene. Ethox or methoxybenzene. But it's just these are so commonly used that it's really like in your best interest to get a good handle on these six at the very least. Okay, so we're going to talk about substituent effects in a second, but just before we do that, there's three different types of positions on a benzene ring. I guess four. You don't really learn this one. This is called an ipso position when it's the position directly attached. These two are ortho positions, so this position and this position. One and two means here and here. Meta positions, the middle positions, para position, the bottom position. And you'll find that ortho and para share general trends and modes of reactivity. Specifically, like when you want to choose a position, generally you either choose meta or you choose ortho and para. And it has to do with the resonance structures, which we'll get into a little bit later on. But yeah, let's get right into substituent effects. Okay. So there's three main effects that you're kind of on the hook for. There's inductive electron withdrawal, hyperconjugation, and then resonance donation slash withdrawal. So donation and withdrawal are the most important ones. Inductive effect is, what you would expect. You have some type of electronegative compound that's pulling electron density by its nature of electronegativity. Hyperconjugation is just when you have alkyl groups, right? And there's orbitals are overlapping such that you're getting a donating effect into this position. Resonance. Okay, this is really important. So this is a quick trick to figure out if something is donating or withdrawing. If you could take this double bond here, move these electrons here, and then move something up, that means that it's withdrawing, right? And if you can't do that, that means it's donating. Because we can see here that if I try to move this double bond up here, then I have too many electrons, so I'm breaking the octet rule, so I need to move these electrons, but they have nowhere to go. Versus here, once I move this, I can move these electrons up. And it's messing with the formal charges, but it's not breaking the octet rule, which is basically the criteria by which we decide donating or withdrawing. And it's good to memorize these, but it's also a lot better to just have a good understanding of that. I think that's a pretty easy trick to do, and I think it'll save you a lot of trouble of memorizing all the different groups involved. All right, let's see. Okay. Reactivity, electron donation increases reactivity. Electron donating groups are activating groups. So activating groups basically just means we are getting a more reactive benzene. And it kind of makes sense why we would have electron donation as increasing reactivity. The benzene ring is a better nucleophile, so it stabilizes the transition state. Electron withdrawing groups tend to decrease reactivity. They're called deactivating groups. So the benzene ring is the worst nucleophile. Because remember, in all these reactions, we have a benzene attacking something else, right? So we want more electron density because that makes it more of a nucleophile, right? Okay, cool. In terms of reaction rates, benzene will be in the middle. That's our comparison standard. An electron donating group means more electron density in the ring, better nucleophile, worse nucleophile. Okay, makes sense. And within electron withdrawing groups, we have like subcategories of like strong, weakly activating, deactivating. Like we have different categorizations, which I do implore you to go through. But I think most of the time, as long as you have a good understanding of this specifically, I think you're going to be able to get it. Okay. So rate determining step, it's exactly what you'd expect. It's exactly what we've seen before. If we have a donating group, it's a lot faster compared to a withdrawing group. Just what we talked about. Worse nucleophile means slower reaction, right? Okay. Ortho and para directing. So strongly activating groups like O, N are attached to the ring with lone pair electrons, right? So they're capable of donating resonance, or sorry, they're capable of donating via resonance. Moderately activating groups are O's or N's attached to the ring with an acyl group, which basically means competing resonance, right? So half the time the electrons are going this way, half the time they're going this way, right? And we get an added on effect here of electron withdrawal. And generally, when we have resonance and electron withdrawal, the major factor that wins is resonance. There's some important caveats to that, which we'll get to as they come up. But generally speaking, if you have resonance, that's the factor that's the most important, and that's usually what's tested. All right, weakly activating groups. So we have alkyl groups donating electrons via hypoconjugation. Aryl and vinyl groups donate weakly via resonance. All right. Weakly deactivating groups. So halogens are weakly deactivating because of poor orbital overlap in the pi bond. Um, so we basically get a really poor resonance, allowing for electron withdrawal to have a much stronger effect. So again, this is 3p and this is 2p. So it's just really, really bad overlapping. It's really, really unfavorable to have a double bond. And if you recall from one of the previous chapters, like that's the same reason why when you talk about acyl compounds and chlorine, you talk about major resonance contributors. The one with the double bonded Cl is not a major resonance contributor because even though the carbon in the middle will have an incomplete octet, it's so unfavorable for us to have a double bond with a chlorine and a carbon. Okay, so all of these are ortho and para directing. So again, in modes of reactivity, we'll attach here, here, or here. Okay. So weakly deactivating groups, okay, meta-directing groups. So these are moderately deactivating groups, which is basically a carbonyl directly attached to the ring, which draws electron density through induction and resonance. Um, Strongly deactivating groups, they also withdraw electrons through resonance, except ammonium, and as well, they do it inductively. Okay, because you see here, there's no resonance. It's only inductive electron withdrawal. But this is a really, really strong group because of the positive on this, right? So if we have a group that's electronegative, a oxygen, nitrogen species that's positively charged, we're going to get really, really good withdrawing. Practically speaking, you're never really going to see a positively charged oxygen here, just because it's not really a very stable structure. We recall, like from last chapter, that nitrogen is okay with having a positive charge on it. It's not optimal, but it's okay. Um, Okay. Effects of substituents on orientation. So ortho meta para. So strong slash moderate activators. Um, so this is nitrogen and oxygen with lone pairs attached to the ring will activate via resonance. So ortho and para are favored because of the substitution effect of donation onto the plus carbon. Ortho and para have four resonance contributors, and meta only has three resonance contributors. So when we talk about strength, stability, and all of that, like the more resonance contributors we have, the the more stable we are, right? Okay. Weak activators, alkyl, allyl, and benzyl substitutions. So ortho-para directing hyperconjugation electron donation is more effective since we have a plus charge on one of the resonance contributors that's next to the substitutor. Weak deactivators like halogens, they can weakly donate via electrons by resonance. These are ortho and para directing or resonance contributors. Moderate and strong deactivators, they direct meta since they're more stable resonance contributors. So basically, pretty much everything is going to be ortho and para, unless you're a really, really strong deactivator, in which case you'll be meta. This is another good way to see it. We can see the partial minuses, we can see the partial positives, right? So if we have a donating group, these are the ortho positions, and this is the para position. So we can see here that if we draw a resonance hybrid, we have partial negatives on each of these points. And if we recall, like this is a nucleophilic attack, right? So we want to attack from the positions that have the most negative electron density. That's why we'll attack from here. These three positions are where a compound would be installed. Versus here, we can see a withdrawing group leaves partial positives on these three positions, right? Which is not optimal. Okay. Considerations regarding substituents. Okay, halogenation, this is the fastest EAS reaction. When the ring has a strong moderate activator, Lewis acid catalyst, you don't even need it. So you don't see here, like, because we have a strong donating group, we're already so nucleophilic that you could be okay with a weak electrophile, right? Because, earlier on we saw the chapters where we needed to make one of the nucleophiles stronger, or the electrophile stronger, right? But because of the fact that we made this nucleophile stronger, we no longer need the Lewis acid, okay? The reaction mechanism is, pretty much exactly the same thing, though. Okay. Friedel-Crafts reactions, these are the slowest of the EAS reactions. So they actually won't proceed with moderate or strong deactivators. So if you have like a nitro group, for example, there you'll just get no reaction. You'll have a sulfate group, you get no reaction. Aniline and an alkyl substituent aniline can't do Friedel-Crafts reactions either. This is because of acid-base chemistry. So what will end up happening is the nitrogen will attack the Al, and we'll just get a complex here. So just keep that in mind. This is one of the cases where nitrogen again will ruin what you're trying to do because of the fact that it's just a really, really good base. Okay, cool. So aniline can't be nitrated. This is causing an explosion. You can look up why if you're interested, but for the purposes of this class, it's not particularly relevant. You just have to know it doesn't happen. There's more issues here. There's side reaction issues. Following side reaction, orthopara, meta-directing. So we can get stuff that moves around. We can get positively charged compounds. The way that we can solve all these issues is by installing a protecting group here. So this is an acyl chloride, right? And we saw earlier that nitrogen will attack this Lewis acid, right? So why don't we use that to our advantage to describe the chemistry that will make a protecting group, right? So once we install this position here, now we're getting withdrawing effects here, right? So these lone pairs here are no longer delocalized, right? Or sorry, they're no longer local to this nitrogen. They're more spread out, which means that they can't perform the attacks that we've been looking for them to attack, right? So now we can go in here, we can install a compound here, a nitro group. And with that, we can remove the protecting group after. As you would expect, the way to remove the protecting group is acid, water, heat, and then we do a basic workup step because we'll have a plus charge compound here otherwise. Okay. So this is the tri-substituted benzenes. Okay. So when you're doing synthesis, you have to keep in mind that the groups you're adding can affect the reactivity of benzene, right? So, like if I wanted to add a nitro group, right? And then I wanted to add an acyl compound after that, I can't do that, right? Because the nitro group will deactivate it. So I'd have to make sure that I add the nitro group first and then I'd have to make sure I add the acyl chloride first and then I add the nitro group. So the order which you do these is pretty important. So let's look here, right? This is the withdrawing group. This is the donating group. We'll actually end up attaching the NO2 here or here. Um, You know why that is? That's just because this is a donating group, right? So it directs ortho to this position. This is the withdrawing group, so it directs meta to this position. And you find out that this is both meta to this and it's ortho to this. So perfect. It can be here or here. For this one, you have a little bit more decision making to do, right? Because this is ortho to this and this. And we know that this methyl group is either ortho or para, right? So here, here, or here. We know this Cl is ortho or para, right? So here, here, or here. So now we need to choose what position to add, right? And if all these three positions are viable based on the concepts of electron withdrawing and donating that we know, the ortho, meta, and para directing, then we move on to basically sterics, right? So we avoid adding to positions between two substituents. So we'll put it here. Um, Makes sense? It's just the most stable place to put it. Okay. And here, sorry. We just would not put it here. You'd get a pretty good mix of these products, I think. I want to say that you get more of this. I think there's some electronic effects that chlorine will have, but for the purposes of what we've learned so far, it's sufficient to say 50-50. Okay. Strongly activating groups substituent will determine the position of an added substituent. Okay. So what is this saying, right? So this methyl group is donating, right? So these are ortho to it. But these spots are meta, which is now like we see a conflicting case between these two. Like you saw earlier that these positions were all like supporting and aligning with each other, right? Like these positions here are well aligned with this and this group. However, now we have a two donating group. So what do we care about more? We care about the stronger activating group, and that's the thing that's going to determine the position. So we're going to add here or here. And even though those positions are meta to this, and methyl is technically ortho slash para directing, this is a stronger electron donating group. So it'll beat out the effect here. So we'll get addition here or here. Okay. Similar strength, substituents yield a mixture of products, right? So if we have two groups that would preferentially add in different positions, we're just going to get a mixture of them because neither of them is really a dominating presence. So you kind of have approximately the same electron density across the ring. Okay. Ortho-para ratio. So we recall from earlier that I told you guys that ortho and para have the pretty much same mode of reactivity. The only difference is there's two positions for ortho versus there's one position for para, right? So probability says we'll add ortho unless we have other factors to consider. That other factor to consider is steric hindrance in the ortho position. If we have a large steric hindrance, we'll favor para. Um, so, you know, we can kind of look through these. I think that there's nothing terribly unintuitive here. We'll get meta addition where we sometimes wouldn't expect because of resonances. Ortho para direction. I think this is all okay. Um, all right. Nucleophilic aromatic substitution reactions, SNAR. So SNAR is pretty similar to EAS. The only difference is instead of the benzene acting as the nucleophile, we'll actually have it acting as an electrophile, right? So all of the trends and all of the directing trends that you learn for EAS are the exact opposite for SNAR, which makes sense, right? Because, in the first category of reactions, the benzene was the electrophile, right? So we were talking about, or sorry, the benzene was a nucleophile. So we were talking about all of the different ways to make the nucleophile better, to add more electron density into the ring. And we know that an electrophile is defined as a lack of electron density, right? Which basically means that it would be opposite to adding stuff into the ring. Okay, but anyway, it's pretty similar to this. So there's a couple conditions for it. First requirement is the leaving group has to be weaker base than the nucleophile, which is, as we would expect, right? Like if we're installing the group here, we need this to be a better leaving group, a weaker base than this. Makes sense. The leaving group must also be ortho slash para to a strongly electron withdrawing group. So we really need to make sure that this is an electrophilic spot, right? So this group here is withdrawing density from this position, and this position, right? Like we saw in the resonance hybrids earlier, there's a partial plus here, here, and here. This partial plus means electrophilic site, right? So we could attack there. Okay. And the more withdrawing groups we have, the better. You can see here that this first reaction had one withdrawing group, and it required a pH of 14 for the deprotonation addition of the HO minus at 160 degrees versus this one is 40 degrees, literally 120 degrees lower because we used two more nitro groups. Um, so it's just to say that these effects are additive, right? The more groups that we have in the particular positions that we want, the better the reaction will be, the less energy required. All right, and this is the general reaction mechanism. So there's a lot more arrows to draw, but it's not too bad. You kind of just follow the electron flow, right? So we know that we install it wherever the leaving group is. So let's do that first. And it goes through kind of a tetrahedral-like intermediate, right? Like if you look at this, that's basically what's going on. So we install here. This double bond goes down here. This comes here. This comes up and then the electron flow goes right back. And again, you might be thinking, why can I not just attach it here and then kick this out? And it's kind of the same reasons that you can do that in E1CB. It's the same reasons that um, we can't do that in a couple future reaction mechanisms. And it's just because the jump in energy between here and here is just simply too high. We need to go through a more stable intermediate, and then we can find this product. Yeah, so I think that about wraps it up for this chapter on aromatic reactions. We'll go through the section chapter in the next video, and what you'll find is it's going to approximately be the same thing. So if you take your time to really go through this properly and understand it, I think you're going to have a much easier time in the next chapter.